Hi everyone, welcome back to another video in the ELEC 2507 lab series. Today we'll be going through the diode lab. So, what you're going to want to do to get started is you're going to want to go through all your pre-lab stuff, fill out this table for your expected values of the voltage on the load, the voltage on the diode, and the current through the load, which is equal to the current through the diode. So once you find all those out and figure out how all these circuits work and answer all the questions, you can go down here and start the lab. So the first thing we're going to do is we're going to pull down a diode. That's from up here. You're going to go and pick a diode here. So once you do that, you can set your RL to 270 ohms. I have 400 ohms chosen down here just for the sake of this experiment. And what we're going to do is it's asking you to vary the variable supply from negative 5 volts to positive 5 volts in variations of 1 volt. So we're going to do that, and then we're going to calculate the voltage, or sorry, we're going to see the voltage through the load. We're going to see the voltage through the diode as well, and then we're going to calculate the resistance of the diode. So without further ado, let's go ahead and we'll run the transient. And we'll bring this back down. To negative 5 volts. So once we're at negative 5 volts, we can see there's no current and no voltage drop across the diode. That makes sense. Negative 4 volts. Same thing. Negative 3. Negative 2. And what I would suggest is having an Excel table open for you while you're doing this, so you can enter your data, and then you can easily plot it that way. Negative 1 volt. So we'll go back around to 0. And then we'll go up to 1 volt. So now that we're at 1 volt, we can see we have 723 microamps, and we can check out our voltage drops if we want by going in here and adding a voltmeter. So we can add a voltmeter here, and we can add a voltmeter across the 400 ohm resistor. And once we have that done, we can see that we have 711 millivolts across the diode, and you can see the negative terminals aren't matched up properly, so we can go ahead and flip this around. Once that's flipped, we can go ahead and run it. Now we have positive 711 millivolts, and we have 289 millivolts across there. And if you add those two voltage drops together, you get the 1 volt that is coming from our source. So that makes sense. That means we have no voltage loss in this circuit. This circuit obeys Ohm's law, and it obeys the conservation of energy from your physics classes earlier. So once you go there, let's go up to 2 volts. You can see the voltage drop increases, not across the diode, but across the load. 4 volts. So you're going to be plotting this data as you get it in Excel, like I said, and then you're going to come up with an IV curve. So once that is done, now that that's done, we're going to move on to the LED portion of the lab. So here, what you're originally going to do is I'll reset this circuit. You're going to put this to 5 hertz. And you're going to put it at 10 volts peak to peak, which would be a 5 volt amplitude. Set the DC offset to 0. So you're not going to need that for now. Alright, so once we're there, we can go ahead and run the transient. And we can see we're viewing the two waveforms on the screen here. We have those waveforms on the screen. When we're viewing our waveforms, it tells us to switch the scale of the scope to something more reasonable. So we'll go around to 200 milliseconds so we can see a nice 2 or 3 waveforms in our scope. So once that's done, we can go ahead to 4.2.4. And here we're asked to find the small signal resistance of the LED. So this is a little tricky with the current software that we have. So bear with me and we'll figure it out. So what you're going to do is first switch this source here, adjust it to a DC source. And from there, we can go ahead and we'll pause the simulation, okay? And then once we have this DC source in here, we're looking to get 5 milliamps of current through the LED. So that being said, we'll go ahead and we'll adjust this DC source until we reach that. So let's go ahead and run the simulation again. So we can see right around 2.95 volts. We're right at the 5 milliamp mark. So that being said, we'll go ahead and we'll switch this back to a sinusoid. And we'll mark down that number firsthand. So remember the 2.95 or whatever your particular voltage is for you need a 330 ohm resistor here. And yep, so just keep that in mind when you're working. So that being said, let's go switch this to a sinusoid. We'll switch that to a sinusoid. And now here's where we'll take the DC offset voltage that we just found of 2.95. And we'll go ahead and we'll put it in here. Once that's done, then it tells us to switch the amplitude to a 1 volt peak to peak wave. So that would be a 500 millivolts wave in here. And then one more thing, we will just delete this wire here and we will add an ammeter so we can see the AC current going through all these branches. So we'll go ahead, we'll switch that to 1 kilohertz, I believe it tells us to switch it to. 1 kilohertz, our amplitude is 500 millivolts, which is 1 volt peak to peak. We have our DC offset set to what we just found in the previous part. And now we can go ahead and we can do these steps around at the bottom here. So if we go ahead and run the simulation again, we can get waveforms for the output wave, we can get waveforms for the input wave, and we can also get waveforms for the current. So we're going to go ahead and add all 3 of those to our scope. And once we have those, the current you can see is backwards right now. So if you want to go ahead and flip that, that would be fine. Go ahead and run that again. So once we're here, we can find out what our ID is through all these branches. So our ID would be the max minus the min for the orange waveform. So the max is 6.58 minus 3.43, gives me around 3.14. So I will go and I will look at the max and the min for the green waveform, which that's just the input wave, so that should be 1 volt as always. So that would be, in this case, that would be the yellow probe. So we're going to do the yellow probe over the blue probe, divided by the current through the AC current through all these branches, which we just found is 3.14 milliamps, and that should be around 20 ohms. So that being said, we'll go look at our purple waveform here. So we're going to have 1.97 minus 1.03, which gives us 0.94, which is around 940 millivolts. So that being said, we'll go 1000 millivolts, which is 1 volt, minus 940 millivolts, gives us 60 millivolts, divided by 3.147, which is the current that we just found, and that's also in milliamps. So if we do milliamps, or millivolts, sorry, divided by milliamps, that will give us a resistance in ohms. And that resistance that I just found for my particular LED here is 19.06 ohms. So that is pretty much spot on to what it should be. That is the best procedure to follow. Don't worry too much about most of this stuff in here. If you really get lost, you can try following it, but the procedure that I just showed you is slightly modified, just because of the lab situation that we currently have. So if you have any troubles with that one, please contact your TA or contact me directly. Alright, so once that's done, we'll move on to the second last circuit that we're creating, and this is the bridge rectifier, also known as the full wave rectifier. So this circuit basically will take any AC input and it does its best to convert it to a DC output. The output is a DC waveform. It doesn't look like one necessarily, but it is a DC waveform. All this extra stuff that I have added here is actually part of the question from the pre-lab in 3.4 here. So if you can figure out what these two blocks do, that is a big advantage to you in this class. Basically, this whole circuit is the whole theory behind everything you kind of learn in this course, and it's one of the bigger application questions that you'd maybe run into on a final exam. So with that being said, we'll go ahead, and the first component that we have here is an AC sinusoid. This is basically it's coming in at a very high amplitude, and then it's being converted down to a smaller AC wave here for the inputs on the diodes, and then that is going toward being fed towards an LED, and this LED is in series with a load resistor. And then after that, we have in parallel with that what we call a filtering capacitor. This filtering capacitor will make the runoff of the DC wave much better. So basically what you can see here, this is the output for the full wave rectifier, and you can see it's every cycle it comes back up, and it's sort of resembling a DC waveform. But we'll go ahead and we'll add this switch here, which then stops our DC waveform from going down, as you can see, like that. And then once we add the third filter, we shouldn't ever really see any dipping. As you can see, it's going down, but it's going down very, very minimally. It's clipping barely at all. And you can see we have almost a constant steady DC output at around 19 volts. Yeah, 19.5 volts or so. So that would be the final DC output, and that's what we could record. But instead of that, what we're going to do is we'll take these two switches off for now. So we'll just have the green waveform again. We'll go back there, and we'll look at the maximum value for the green waveform, which is 23.4 volts. And to measure the average DC output, what we could do is we could go into the theory behind our full wave rectifier and figure out that the voltage, the DC voltage, is 2 times the maximum voltage divided by pi. So that's the same as 0.637 times the voltage max. So we'll go back to that circuit. Where is it? It's here. And we'll take that 20.3 times 0.637 gives us 12.93 volts. So, in the end, my average DC output for this full wave rectifier is around 12.93 volts DC. So those are the measurements you need to take here. Yeah, other than that, you should be fine. Make sure you're keeping the current in the LED below 10 milliamps, so it's not. You'll see if you're putting it higher than that, you'll see the LED actually starts blowing up. It makes a little fire animation, and you'll see it not working properly. So you'll notice that very easily. And last but not least, let's do the circuits shown in Figure 7. So those are these ones. So we're gonna again just connect the transformer output, which we don't really need the transformer output in this case because we already have a sinusoid of whatever amplitude we want, to a 1 kilohertz. And then in the first case we're gonna do a single diode. Second case we're gonna do 2 diodes, one in the forward direction and one in the reverse bias direction. And in the third case we're gonna do 2 stacked in the reverse bias direction and 2 stacked in the forward bias direction, and we're going to see the resulting waveforms for all 3 of those circuits and basically what's happening in all 3 of those. So without further ado, let's go ahead. Here's the first one. It's a reverse bias diode. You can see 1 kilo ohm, and if I know it's hard to see here, but at the falling edge on the wave, so where the wave is in the negative half cycle, that is actually when this diode is conducting. I know it's very tough to see that, but if you can notice, when the sine wave is going down below here is when the diode starts to conduct, and it actually conducts in the reverse direction. So these half cycles would actually be in the negative half cycles for the diode. Just when you're drawing it out on a graph, make sure you show that. Yeah, I guess that's it for that circuit. Next, we have the one with 2 diodes, one in the reverse bias, one in the forward bias. You can see in the positive half cycle, the forward bias diode is conducting, and you can see in the negative half cycle, we have the negative reverse bias diode that is conducting. And you can see the waveform here is very square, and the reason for that is because one of the diodes is conducting at each half cycle, and it's cutting the top off because it can't get any higher than 700 or minus 700 volts, or sorry, millivolts, because that's the bias across the diode. Yeah, and then in the third circuit, we have double the diodes. So now in this case, in the positive half cycle, we have we have two diodes dropping, and then in the negative half cycle, we have we also have 2 diodes dropping, right? So in this case, we should have hey, we should have positive 1.5 and negative 1.5, which is two diodes that are connected in series, and those are the drops from each of them at each particular moment. So in the negative half cycle, we have negative 1.5 volts dropping across both of these diodes, and in the positive half cycle, we have positive 1.5 volts dropping across these two diodes. Should be fairly self-explanatory. I hope that helps to finish your lap. If you have any questions, don't hesitate to contact me or your TAs. Good luck. Bye-bye.